Welcome back, everyone. Let me introduce today's speaker, Ferenc Karsai. He joined VASP after doing a postdoc with Peter Blaha around the same time that VASP became a company in 2017. By training, he's a theoretical chemist, and he's an expert in many areas of VASP, including the application of them. For instance, electron-phonon coupling, core excitations, and molecular dynamics in general. But his current main focus is as a developer in machine-learned force fields, and this is what he'll talk about today. So I'm very pleased that he takes the time to present this introduction today. Go ahead, Ferenc, the stage is yours.
Thank you very much. So welcome, everybody. Here I'm going to talk about chemical reactions using machine learning force fields. So density functional theory, as shown here on top with the Kohn-Sham equations, has been the workhorse for computational solid-state physics and chemistry for decades. It is quasi-ab initio, despite a few parameters, reasonably fast and reasonably accurate. But unfortunately, if going to finite temperature, that means mainly motion of atoms, for example by molecular dynamics, it is too slow. For example, 100,000 time steps, which often belong to only a few tenths of picoseconds, will take months to simulate. Additionally, this is only on small to medium-sized unit cells with around 2,000 electrons at maximum. There are many classical workarounds like cluster expansion, coarse graining, etc. And for us, the most important, force fields, to which we come here. Classically, force fields have a physically intuitive and at the same time computationally inexpensive form. Famous examples are the Lennard-Jones potential or the Axelrod-Teller. With them, one can typically go up to even millions of atoms and for several microseconds or more in the calculations. But of course, this comes at the price of very limited accuracy in the calculations. Force fields can be further optimized by parameterizing them to many DFT calculations. Making these force fields is very cumbersome, and it can easily take several months to make a decent one. Also, the accuracy of these force fields is mostly still not good enough compared to DFT. For example, in the popular methylammonium lead iodide, or MAPI, the best force fields can't describe the correction rotation of methylammonium molecules. So we need a force field that retains the accuracy of DFT, but is approaching the classical force fields in terms of efficiency. This is machine learning force fields, the new sledgehammer, if you want to say so, which depending on the training can very closely resemble the accuracy of DFT. At the same time, it is close in execution time to parameterized force fields. Another strong point is that machine learning force fields are very easy to make compared to parameterized force fields. Here you can see the efficiency of the machine learning force fields. From bottom to top, the computational efficiency increases. In principle, the accuracy with respect to experimental data would go vice versa, but the machine learning force fields are an exception. They are very close in accuracy to the underlying method they have been learned on, and if we would use some beyond DFT method as a training data, we would end up with a force field that is much more accurate than DFT calculations. But going back to efficiencies, we see that DFT needs seconds to hours, depending on the computational parameters. Our machine learning force fields only need around a few milliseconds per atom per core. This is at least 3 to 4 orders of magnitude faster than DFT calculations, but typically even more, up to 6 times faster. So what I mentioned before, that 100,000 time steps for DFT would need several months. These calculations are reduced to a few hours with machine learning force fields. Just a note, classical force fields are still and will be always faster than machine learning force fields. So with that, let's talk about the machine learning force fields. Here are the basic ingredients of this machine learning force fields. First of all, you need a set of reference configurations. For example, this can be a set of single point ab initio calculations or a set of snapshots taken from molecular dynamics simulations. The reference calculation set consists of multiple structures. Each structure consists of the ion positions and the lattice vectors. It also contains the energies, forces, and stresses from ab initio. The idea of machine learning force fields is now to make an algorithm in which we learn how to get from ion positions and lattice vectors to energies, forces, and stresses without actually performing the ab initio calculations. The basis for this training is the reference dataset. VASP offers here specialty, which is on-the-fly training, but you will hear about this later. The other two ingredients are now concerning the inner working of the machine learning force field itself. One is that the machine learning force field needs a good representation of local environments. We will discuss this in more detail in a moment, but for now let me just note that we cannot use the Cartesian coordinates of the atoms. They do not incorporate the symmetries like rotational invariance. The last ingredient is the actual machine learning algorithm, which must be a method that can reproduce highly complex functions, in our case the potential energy, from a high-dimensional input, the descriptors. There are many algorithms out there, the most prominent being neural networks. VASP is not using this algorithm, but the so-called kernel-rich regression. So let's get more into the details of VASP machine learning force field method. The key assumption of many machine learning force fields is to write the potential energy as a sum of atomic energies. Note that there is no physical justification for this, and DFT will not give you per atom energies. The per atom energy contributions are the output of a machine learning algorithm. The input is the local environments, that is the position of neighboring atoms. In our case, a cutoff radius is used, so neighbors within a certain cutoff radius are relevant. Here comes a crucial point. What would happen if we would use the Cartesian coordinates directly as input for the machine learning function u? It would not know automatically anything about translational or rotational invariance. We would have to provide this information in training dataset. This would require a huge amount of data, making the method impractical. In order to avoid this, we insert a so-called descriptor between the coordinates and the energy function. This descriptor should take the invariances into account. It will transform the neighbor ion positions relative to the central ion into a set of numbers. These are already invariant with respect to translations and rotations. This will be the input to a machine learned function u. So let's talk about how to construct the atomic environments. One basic idea is to expand the atomic density distribution around each atom. This distribution rho is invariant under translations, but not with respect to rotations. So we need some variations that introduce also rotational invariance. These are pair and angular correlation functions. The pair correlation function describes how likely it is to find an atom J at the distance r from a central atom I. And the angular correlation function describes how likely it is to find an atom J at distance r and another atom K at distance S from the central atom I and the angle between them theta. It is noteworthy that if the atoms J and K are the same distance away with angle theta equals 0 between them, then the angular descriptor gives the same information as the two-body descriptor. Now we will see how these descriptors are constructed. First, we expand the density distribution at two-body auxiliary basis C with indices ILM. I will call them C and LM since the central atom I is implicit. These C and LMs are expanded into a radial basis chi and a spherical harmonics YLM here. For the radial basis in VASP, we use modified spherical Bessel functions. So the rest of the indices and LM are the number of radial functions and spherical harmonic indices L and M. The auxiliary basis functions C and LM are the coefficients of the pair and angular descriptors. For the pair descriptors, we take them directly. And for the angular descriptors, we take the products of two C and LMs. Typically, we have much more angular descriptors than radial descriptors. The number of angular descriptors is between 400 and 2000 usually, while the number of pair descriptors is around 8 to 12. So now we come from descriptors to the fitting problem. We start by asking the question, how should the function for the energy contributions U look like? Actually, one way of tackling the problem is to use a neural network here, where input nodes are descriptors and the output is the energy contribution U. However, VASP follows a different path. Let's assume we would try a standard regression method here. So we represent our function U as a weighted sum of basis functions. Here we would need a complete set of functions with all combinations of x and y and the powers. The problem is of course even amplified for the derivatives, which are needed for the forces. So this would also mean we need to construct in the end a complete set of functions in many, many dimensions. This is of course not feasible, so we have to come up with a solution. And the solution is like, for example, the so-called kernel trick. Instead of a huge set of functions, we build a kernel that allows us to compare the current environment of interest to a previously determined set of reference environments. So the kernel should be a potentially nonlinear function that measures the similarity between the descriptors x and the descriptors of the references xib. VASP employs polynomial kernels. This builds the dot product of local reference configurations xib and our target vector xi. Then this product is raised to the power key. So when the two vectors are orthogonal to each other, or in other words, are not similar, the dot product becomes 0. Otherwise, if they're fully similar, the dot product becomes 1, since we use normalized descriptors. Another good thing of this kernel is that we have determined that xi equals to 4 is always good, and with that, we don't have to set any parameter for this kernel. As another example, we have a look at the Gaussian radial kernel. As you can see, it just measures the distance of two vectors xi and xb, and then puts a Gaussian on it. So when the environments are identical, the kernel is 1. If the two descriptors are different, the Gaussian approaches 0. Advantage of this doesn't need normalization of the descriptors. So let's visualize the fitting procedure in the next slides on a simple example. Here we use the Gaussian kernel to determine the total energy. In blue, we have an unknown function that we would like to predict, which is the total energy. We have here a one-dimensional descriptor on 5 reference points in red, where we know the exact value of the function. We use these 5 points as our references xib and overlay them with Gaussians with equal height. So now we can fit the regression coefficients wib, which weigh the Gaussians differently in the end. Here you can see the different heights. And finally, if you lay then the functions through these Gaussians, we can nicely fit this function with this dark blue here. Okay, so let's come to the actual fitting itself. In principle, we have to solve a simple least squares problem as seen here in the top. In that equation, capital phi is the so-called design matrix. It contains the kernels and the derivatives of the kernels for each central atom. It also connects the weights W with the target vector Y. In one dimension, the design matrix contains all entries for energies and forces for each structure. That means, for example, for 500 training structures and 100 atoms in each training structure, that would be 500 entries for energies, plus 500 times 100 times 3 entries for the forces. That's 150,000. And Y, so this Y has also this number of entries since it contains the energies and forces from the training structures. The other dimension of the matrix contains the local reference configurations. So these would be the columns. So if we assume these 500 local reference configurations and take the approximated 150,000 lines from the previous assumption for the training structures, we end up with a hugely overdetermined system of 500 unknowns and 150,000 equations. This suggests that some kind of regularization is required. So let's come to the employed regression methods in VASP. One is the Bayesian linear regression as shown here in the center. This equation is solved via LU factorization so that no inversion is needed, since inversion would make the condition of the problem worse. The normal equation shown involves regularization by the division of sigma v squared divided by sigma w squared. It also involves squaring of the design matrix, which is also the covariance matrix. But this squaring also squares the condition number, which leads to a worse accuracy of this method. But this method is fast. So we use it in on-the-fly, where fittings have to be done very often, and the timings of the fittings are critical. The more exact way to do the fitting is by using the pseudo-inverse. Here first an SVD decomposition is made, and by rearrangement of the decomposed values, the weights can be calculated. The nice thing is that this does not require any squaring of the design matrix phi. This results in a much better conditioning than in the Bayesian linear regression. And this further results in a significantly improved accuracy compared to Bayesian linear regression. This means sometimes up to 30 to 40%. Another nice thing is that regularization can here also be employed, as shown in the third equation here. The drawback of this method is that it is computationally expensive. Hence, we will only use it at the end for refitting to finalize the force field before we can start with the production runs. So here's a wrap-up of what was shown about the methods employed in VASP until now. The total energy is the sum of atomic energies. These atomic energies are the sum of weighted kernels. We have two waves of fitting, the less accurate but fast Bayesian linear regression, and the more accurate but slow pseudo-inverse using SVD. Next, kernels measure the similarity between target atom and local reference configuration IB, and VASP employs polynomial kernels. Descriptor xi describes local environment of atom I up to a cutoff radius, and xi contains 2 and 3 body descriptors, which are invariant with respect to translation and rotations. So next, I want to give an outline about the machine learning force field procedures in VASP. The commands in the brackets are the respective INCAR tags and will be mentioned later. First, acquire the database via on-the-fly learning. Second, optionally reselect the local reference configurations. Third, refit the force field using singular value decomposition. But as already mentioned, we do this since SVD can give significantly improved accuracies in the force field. And also by refitting, we enable the fast force field. So this step is a must do. So next, as force, check the accuracy of the force field. A guideline for the root mean square error of the force field is an error below 5 millieV per atom for the energy and an error below 100 millieV per angstrom for the forces. If at this point the force field is not accurate enough, it possibly needs more data, so for that repeat the previous steps. As the last, if the force field is okay, one is ready for the production runs. They are not discussed in this talk since they are really about advanced molecular dynamics methods and easily fill multiple talks on their own. So now we come to the point where we have the methodology and order of tasks established and want to go into more detail about the acquisition of data. A kernel-based machinery requires two data sets. On the left, we have the training data set. It consists of the structural data, that means ion positions and Bravais lattice, which are required to construct the descriptors, and also consists of energies, forces, and stresses for each of these structures required as the reference values in the fitting. On the right, we have the local reference configurations. These are specific to the kernel method. They are atomic environments used as references to construct the kernels shown before. They are also saved as descriptors, and they are usually chosen from amongst atoms in the training data. So now that we know what we need, there are two questions. How do we create the training database, and how are the local reference configurations extracted from the training data? The brute force approach would be to run ab initio molecular dynamics simulations and extract the data from those. That would mean, for example, we run an ND for 100,000 steps and extract the structure at every 1,000th step to possibly cover a large phase space. As already mentioned at the beginning of this talk, this would be computationally very intensive and could easily take up several months. Additionally, we would anyway end up throwing away the majority of ab initio calculations. So why not already select the right ones in advance? This could be attempted by Monte Carlo sampling, but we most likely would not sample from the right phase space as from molecular dynamics. So to sum up what we need for a good sampling algorithm, it has to go over long trajectories and it has to perform ab initio calculations only if necessary. The solution for this is on-the-fly learning, or also called sometimes active learning. Here I'm going to show how the on-the-fly learning algorithm in VASP works. So we start by reading an existing machine learning force field. That means we check if we learn from scratch or have a continuation run. Then a molecular dynamics run with the desired physical conditions is started. The following steps are then carried out within this molecular dynamics calculation. First, we predict the potential energy surface. That means energies, forces, and stresses by the existing force field. And here we also predict uncertainties, the sigma squared here. These uncertainties are calculated by the Bayesian theorem and are the variances of the forces that we use. The predictions are compared to some threshold that can be either automatically updated or is kept constant. From this point, two branches within the flowchart are possible. Here, this and this. One is where the predicted errors are above the threshold. In that case, we do a first principles calculation and add the data to the training set. After that, local reference configurations are selected from these training structures, and the force field might be retrained. The retraining is not done every time, but usually after a block of data is filled with new training data, by default 5. This is to minimize computational overhead. After that, the atomic positions are updated, the next MD step is calculated. The second possibility is that the predicted errors are below the threshold. Here no layering occurs and algorithm is driven, so the MD is driven by the force field. With increasing time, more and more ab initio steps are skipped. So with this algorithm, around 99% or more of the ab initio calculations is skipped in total. Also, the whole algorithm is fully automatic without requiring any human intervention. So let's have a look at the Bayesian error estimate in a practical calculation. On the right, you see solid silicon heated from almost 0 Kelvin to 800 Kelvin. Just a small remark, never set the beginning temperature to 0 Kelvin in VASP. So on the x-axis of the plot, you can see the calculation ran for 20,000 time steps. On the y-axis, you have the error in forces. Now let's have a look at the curves. The red curve is the average fitted error. That means error from ab initio calculation versus machine learning force field. You can see from the steps that this is only updated if the force field is freshly trained. The green curve shows the Bayesian error estimates for the forces at every step, and the blue curve are the thresholds for the learning. Here they are calculated as the mean of the Bayesian errors for the last 10 steps where ab initio calculations were carried out. As a consequence, one can see that the thresholds somehow follow the Bayesian error. What can be greatly seen from here that the Bayesian errors strongly underestimate the values of the real error. This is the case because they only estimate the uncertainties from the training data, but not the errors related to the fitting model. That means descriptors and etc. Nevertheless, the Bayesian error captures the trend of the real errors and is enough to have a good sampling. It should also be mentioned that heating runs are required, otherwise the threshold can be stuck at the beginning of the calculation, resulting in too few sampled structures. This is because at the beginning of the calculation, we have a bad force field, a low number of local reference configurations, and the error is built up from those. And if you predict the error to be much larger than what it should be, it can be that it's never exceeded by the predictions later. This kind of plot for the errors shows a typical behavior of an average system. Next, here I show another example. where the plot looks quite different. This is carbon monoxide at the rhodium surface heated from nearly 0 Kelvin to 1000 Kelvin. This is a continuation run of a pure rhodium surface. If you look only at the threshold, you see that it really behaves differently compared to the solid silicon before. So here's solid threshold for solid silicon in blue. Here's the new threshold. There the threshold, so in solid silicon, the threshold was increasing with increasing temperature. Here you can see it goes up and down and has a maximum even, somewhere at the beginning at 10,000 steps. You will also see that, as before, the real arrows would be higher on average than the Bayesian arrows. What we see here very dominantly are a lot of these green spikes, which is different to the curve of solid silicon. These are related to movements of the carbon monoxide molecule, which result in configurations that were not seen before and are quite hard to learn. That means we sample a lot, but in the end, we end up with a good force field with low errors in force. So this was a different example of how an on-the-fly learning plot can look like. So let's talk about a strategy for calculations where we need to describe non-equilibrium states in the production runs. For that, we need to sample these states for training. Inspired by the temperature ramps which you just saw, we can also introduce a ramping, or in this case, not really a ramping, but a driving of a reaction coordinate. The change of the reaction coordinate is simply controlled by the tag increm in the INCAR file. This tag controls the rate of velocity at which the reaction coordinate defined in the iconst file is changed. This method is also called slow growth method. Here is an example, the zeolite chabazite with an acetaldehyde adsorbed and it is chosen. We see here circled in yellow the acetaldehyde ion which contains 2 carbon atoms in brown, 1 oxygen doubly bonded to one of this carbon in red, and 3 hydrogen atoms in white. The movement of the acetaldehyde molecule is what we want to control. For that, in the icons file, we would set 2 distances, which are selected by the capital R here, and the superposition, which is selected by the capital S. The 0 at the end means constraining of these coordinates. The first distance is chosen as the distance between atom 3, which is this carbon, and atom 25, which is the oxygen atom of the host. The second distance is chosen as the distance between the 2 carbon atoms. The weights of the superposition are defined by the numbers here. So in this case, we keep the difference between the distances constrained. Lastly, I should mention that these kind of trainings are done at constant temperature. So here I show how the key stage of such a slow growth simulation would look like. At the beginning of the reaction, in the reactant state, the carbon atoms are far apart. Then we come to the state that we are actually interested in, the transition state, where the 2 carbon atoms came close to each other, resulting in a local maximum on the potential energy surface. The third state here is one of many possible product states and is possibly not always reproducible. So by going through 15 to 20,000 steps of training using the slow growth, we see that a lot of learning is done throughout the calculation in this plot. Compared to rhodium CO and of course solid silicon, the Bayesian errors here are even more above the threshold. See it here. This is because previously we dealt with equilibrium phases. Here on the other hand, we have to learn transition states or non-equilibrium phases. Additionally, the calculation parameters are kept low here, since this is only an example for demonstration purposes, which makes learning the more noisy training data even harder. This additionally contributes to the frequent learning. So with this, I showed you a way of sampling for advanced molecular dynamics methods, where you often need to describe non-equilibrium states. So here, let's wrap up what I've shown about on-the-fly learning. We need to collect training data in a clever way, otherwise it would take too much time to collect it, or it would not collect from the required phase space. For that, VASP offers the on-the-fly training procedure. It uses the Bayesian variances to estimate errors of the force field. These Bayesian errors are usually lower than real errors, because Bayesian errors only estimate the error in the training data, but not in the model. Nonetheless, it is a good estimator, since only trends are enough to capture for a good sampling. Next, one should use heating runs in VASP for optimal samplings. And alternatively, for non-equilibrium states present, for example, in chemical reactions, use the slow growth method for on-the-fly sampling. So next, we come to the VASP-specific usage of the machine learning force fields. Here I show the main files of VASP. Let's start with the MLlog file. This is the main output file of the force fields. It contains an overview of all important parameters and shows the errors and other analytics at every force field step. For example, the error plots I have shown you before were extracted from the MLlog file. The format is made such that it is easily grabbable, and for example, one simply types grep err MLlog file on the command line, and real errors at every time step are given out. Okay, next are the MLAB and MLABN files. They contain the whole training data and also the local reference configuration list. The capital N at the end stands for new, and the MLABN file is the output file, while the MLAB variant is the input file. Otherwise, these files are identical, and the MLABN can be copied to MLAB to use it as an input. The next file is the MLFF or MLFFN file. It contains the force field. It is in binary format, but it also contains a human-readable header containing the most important parameters of the force field. The input-output usage of MLFFN and MLFF is analogous to MLAB and MLABN. And finally, there is the MLREG file. It contains all the ab initio energies, forces, and stresses together with the predictions by the force field. This file is not an essential file, so I am not going to talk more about it here. So on these upcoming pages, I will talk about the control of the machine learning calculations. The machine learning calculations are enabled and controlled via the INCAR file. All machine learning related tags have a prefix ML and then underscore. So let's start with the first parameter, LMLFF. By setting this parameter to true, the machine learning calculations are enabled. Another parameter is ML mode. This selects the available execution modes of the code. The most important modes are train, refit, and run. Train runs the on-the-fly training mode. Refit is needed after this mode to refit the data via SVD and hence obtain a better accuracy. More importantly, it also activates the fast execution mode for the production runs. I mention this here because this fast execution mode gives a force field that is 20 to 100 times faster than the force fields that come out from train or select. With these two texts, you could already run a machine learning calculation, but they're both mandatory, of course. But the next two parameters here are also quite important. That are MLMB, the maximum number of local reference configurations, and MLMConf, the maximum number of training structures. The value for these need to be set since many memory-consuming arrays need to be statically allocated. The reason why we use static allocation is because some of the arrays are using shared memory, and we found out that the shared memory arrays make huge problems on some systems when reallocated. Hence, we want to allocate them only once at the beginning and try to anticipate how large they can get. So with these 4 tags, many calculations should work nicely in all operation modes. On this slide, I show the control of the descriptors. The important tags are only the cutoff radii for the radii and angular descriptor. The default values for the descriptors were determined from experience on many different calculations and applications. We can use substantially larger cutoffs for the radial descriptors because they are computationally very cheap. Hence, while at the same time, we would improve the quality of the force field noticeably. The defaults for the cutoff radial work usually very well. However, in some systems, optimizing the force fields can be really beneficial. Like, for example, liquid water needs an angular cutoff of 4 angstrom only. Next, we come to some on-the-fly parameters. The first parameter, MLI criteria, selects whether the error threshold is automatically updated or not. That means a constant value is used. Constant value is usually only set if a target force error should be achieved. I would advise to do this only for the more experienced users. Next, the second entry, MLCTI force, sets the starting value or the fixed value of the threshold. This is needed in continuation runs of on-the-fly training. The third entry, MLCX, allows to control how many ab initio calculations are executed. This tag is usually more for the experienced user, and I only wanted to mention its existence here. Next, we have some additional training settings. The first 3 tags, starting with the W after the prefix, control the relative weight of the energies, forces, and stresses. Setting the weight for forces has usually a small impact because we have anyways much more lines for the forces than for the energies and stresses. This means that they are anyway much stronger weighted. I should mention that setting the weight for the energy is very important in free energy calculations. By increasing the weight by a factor of 10 to 50, the accuracy of the energy can be improved by a factor 2 to 3, while at the same time the accuracy of the force fields and stresses remains almost the same. The last parameter, MLI-GoLinRec, chooses the fitting algorithm. While the choice of the fitting method is important, the user does not have to worry about this tag since it is automatically chosen by the ML mode tag. I just wanted to mention the existence here. Next is an important page. Here I want to mention some important parameters to set during the production calculations. This is important because chemical reactions will usually involve a lot of long MD calculations, and a lot of time and computational resources can be wasted with the wrong settings. First is if you have several elements in the system, which you will almost surely have in chemical reactions, use the reduced descriptor here. In contrast to the regular descriptor on the right, it depends on the capital on one capital J prime here, less, so it's missing here. This is the number of elements, so its number depends linearly only on the number of species instead of quadratic. This will often lead to a significant increase in computational performance. However, this increase is not linear with the number of species. Why? Because not all parts of the code depend on the descriptors. The drawback of this descriptor is some accuracy loss, but the accuracy loss is often at around only 5 to 20%, which is almost always worth the bargain. Another thing which we saw with this descriptor is that it can be sometimes more stable than the regular descriptor out of the box without tweaking of the regularization. With stable, I mean that when running long trajectories, the force field is less likely to explode or go onto an irreversible deformative trajectory. We don't fully understand this behavior until now, but it has probably to do with the simplicity of the reduced descriptor compared to the original one. At the moment, the reduced descriptor is only available for refitting and then production runs, but in the next VASP release, 6.5, it will be also available in the training mode. Since there we use an algorithm for prediction, which depends really quadratically on the number of elements in the descriptors, the speed up for the predictions will be truly linear with the number of species. Since in the training runs 99% of the steps is spent for prediction, the speed up there will be significant for the total learning time. Another thing is that calculation and writing of the pair correlation function during production runs should be turned off. This is done via ML output mode equals 0, which will become the default in the next release anyway. But here I want to mention it. This is very important since the calculation of pair correlation functions can be many times more expensive than the force field step itself, and the pair correlation functions can be obtained a posteriori via the xk file also. The next thing is that output should not be made every MD step, since the writing to files can become expensive compared to the force field prediction. This is controlled by ML outblock, and typical values for ML outblock in long MDs are 10 to 100. Another benefit from this is that the size of the output file is decreased and handling becomes more easy this way, of course. Next, I also want to mention some key parameters for the MD calculations combination with force fields. One should stick to the following points for on-the-fly learning. If possible, always use NPT ensembles with a Langevin thermostat. The NPT involves small volume fluctuations during the learning, which stabilizes the force field, and the Langevin thermostat ensures the best ergodicity from the available thermostats. Also use large enough cells to reduce volume fluctuations. Increase the energy cutoff by 30% to reduce Poulet stress of finite basis set problems. If the Bravais vectors increases by more than 10%, stop the calculation and restart from that point or from the last contra to ensure proper size of the basis sets. For surfaces, keep the box fixed. For liquids, only allow fixed shape volume fluctuations. I've witnessed myself many times that if the lattice is allowed to freely relax in calculations involving liquids, the structures can irreversibly distort into rod-like structures. These calculations give then, of course, total garbage results. The last thing is that I want to mention is that if somebody needs the extended molecular dynamic features within labs for production runs, our force field will be available in labs with the upcoming VASP 6.5 release. For that, we rewrote parts of the code in C++, and the force field can be directly interfaced with LAMPs. So here, let's wrap up what I've shown about the usage and control of machine learning force fields in VASP. The main output file is the MLlog file. It contains all the used parameters and the error information at each step. The information is easily accessible using grep on the command line. VASP uses one human-readable file for the training data, the MLAB or MLABN file, then one binary file containing the force field, MLFF or MLFFN. The calculations are controlled via the INCAR file. 4 tags are required. These are LMLFF, the on and off switch, ML mode, which selects the calculation type, MLMB sets the maximum number of local reference configurations, and finally MLMConf, which sets the maximum number of training structures. Most default parameters are broadly applicable and don't need to be changed, but can be tweaked if required. And last, MD calculations involving machine learning force fields need carefully chosen MD and production run parameters. These parameters are also mentioned in the best practices page on the VASP wiki. So after we have obtained the force field, we come to the point where we need to test the accuracy of the force field and verify that it is working for our problem. For that, I have this hierarchy of tests here. The first thing to look at is always the training set errors. If the forces are not accurate enough on the training data on which they were fit, they will be most likely only worse on the test data, or more generally on data that is not within the training data. If at this point I'm not satisfied with the accuracy of the force field, I need to go back to improve the training. Next, the first test specific for chemical reactions would be to do static transition state tests using the improved dimer method and compare the DFT results to machine learning results. Since this only involves a couple of static DFT calculations, it is computationally very cheap. This is really the first test that one should make, because if the force field can't reproduce well the static transition, then that force field will surely not reproduce transition states from molecular-like dynamics. In that case, again, one should go back and improve the training on the force field. The third test, which is probably the simplest in terms of human intervention, is the spilling factor. This is a quantity that measures the extrapolation, hence the quality of the force field. It can either be applied to a test set or for monitoring during production runs. This feature is not available in VASP 6.4.3 and will be available in the next big release 6.5. Last, we have test sets. they are computationally the most expensive. With test sets here, I mean calculating an observable in a small to medium collection of structures or ensemble, whose structures are not included in the training data. These collections are then calculated with DFT and machine learning, so that one can directly compare the machine learning results to DFT and evaluate some statistics on them. The advantage of this is that it gives errors directly on energies, forces, and stress. And these errors are comparable then directly to the training errors. So let's come to the training errors. Training error is the error of the machine learning force fields compared to the reference data on which the training was carried out. It is easily accessible from the MLOG file via grep. For that, one simply can write grep err mllog file in the command line. This gives a header that I have cut here a little bit. The header starts always with a hashtag, and it also gives the root mean square error of the energy, forces, and stresses at each MD step. So what are usually desirable training errors? Below 5 millieV per atom in the energies and below 100 millieV per angstrom for the forces. Here I show a short recap of the dimer method, or the improved dimer method. It is presented in detail in another presentation. The dimer method works with two images, which are referred to as the dimer. The two images are displaced by delta R from a common midpoint R0. And next, the dimer axis is rotated parallel to the direction with lowest curvature within this midpoint R0. Then the dimer is moved along this new axis, along the unstable direction up to the energy maximum. And at the same time, the energy is minimized in dimensions perpendicular to this axis. These steps are repeated until a given desired convergence threshold is reached. Since the dimer method is computationally not expensive compared to full molecular dynamics calculations, it can be easily done with DFT. Hence, this method can be run with both DFT and the machine learning force fields, and the results can be used to compare the two. This is done here on the right for the previously shown acetaldehyde in chabazite. We see quite nice agreement and can say that this force field has passed the first barrier for usability. Next, I will introduce the so-called spilling factor. It measures the projection of a structural environment, or descriptor xi, onto the local reference configurations of the force field xib. The projection is done via the previously introduced kernel functions. And these kernel functions measure the structural overlap of xi and xb. Since we use normalized vectors for x, we end up with values between 0 and 1 for the spilling factor. Higher values, so towards 1, mean that the current structural environment is not well projected onto the local reference configurations, and the force field is more strongly extrapolating for that structural environment. More extrapolation means worse accuracy of the force field. In contrast, lower values mean the force field is less strongly extrapolating and hence more accurate. It should be mentioned that the spilling factor is highly dependent on species, and that looking at absolute values to compare different compounds will probably not work. The spilling factor, for example, is rather good to monitor its value during a molecular dynamics run and to see how often the values spike to judge the accuracy of the force field. So next, I come to the usage of the spilling factor. So how is it controlled? Very simple. We have one tag, MLIERR. This tag sets the number of the MD step at which the spilling factor is repeatedly calculated and printed out to the MLOG file. Here in this example, it would be calculated and printed out at every 10th MD step. In terms of computational cost, the spilling factor is often in the ballpark of the evaluation of the force field for a single molecular dynamic step. But fortunately, we don't need to calculate the spilling factor every step, because after a few consecutive steps, the structure has not really changed. So it's full enough to obtain it every couple of tenths or hundreds of MD steps. This way, we can bring the computational overhead down significantly. Typical values for MLERR, so MLIERR, are 50 to 100 in long MD runs. The output of the spinning factor is like for all other values via keyword to the ML log file. The keyword is SFF, which stands for spinning factor final. The output that you get is shown here. It shows the number of MD steps again, and the most important quantities are probably the maximum spinning factor among all atoms and the mean of the spinning factor, or the arithmetic mean of the spinning factor amongst these atoms. So let's use the spinning factor to analyze the accuracy of our force field. Here I have rerun the previous slow growth calculation in a production mode. That means force field only. Although I start from the same structure and use the same random seeds, I will end up with a quite different trajectory for several reasons. I used a finished and completely trained force field instead of building it up from scratch during the run. And I ran on multiple cores, so order of summation plays a role together with rounding errors. And consequence of all this also error propagation. So this trajectory is far enough from the training trajectory to be a good test set, but not too far since I enforced the same reaction coordinate due to the slow growth approach. This way, this is a nice test for the accuracy of the force field. Just a side note, running this took me a few minutes, and I only had to grab at the end of the calculation. If I would have sampled a test set from this trajectory, it would have taken many hours to complete, and I would have had to manage multiple files, etc., much more human intervention. Get back to the figure. I plot here the arithmetic mean of the spinning factor for each atom against the molecular dynamics step. On the left, we have the reactant states. We see several peaks, so those configurations are not so well described by the force field. But that is fully possible because in this force field, only 5 picoseconds were trained on the reactant. The red line shows the transition state. This was sampled in a slow growth calculation, and it seems that the sampling was good enough because spinning factor is quite flat here. On the right, we see a very strong increase of the spinning factor during the end. Here, the structure goes probably into one of many possible product states, and this product state was possibly not well sampled. But for this example, we don't care about the products, but rather about the reactants and transition states, so up until here. So let's get back to the reactant states. I've taken a force field and continued training on the reactants for an additional 20 picoseconds to improve it. So by doing this, we get this green curve, and we see that the larger peaks vanish when I rerun the slow growth calculation with the improved force field, and we have successfully improved the quality of the force field altogether. I should also mention that additional to, instead of the 20 picoseconds calculation, I could have added the structures which are identified by the spinning factor of being bad. However, in that case, I would need to reselect the number of local reference configuration by setting ML mode is equals to select. This can be a quite time-consuming task. Last, I want to give you an example of test errors. Here we have solid cesium lead bromide. It was trained between 250 and 400 K. It was not trained particularly long and with well-converged DFT parameters, but it was made for demonstrative purposes within the stock. For different temperatures, I ran then 50,000 time steps and selected evenly 100 structures on each temperature. Then for those 100 test structures, I ran ab initio force field calculations, calculated the root mean square error of the forces, which is shown here in the plot. The test errors at each temperature are shown in the blue, and the training error is shown as the dotted line. So what we see is that with increasing temperature, the test error increases. Here at 300 K, the test error is similar to that of the training error, and up to that temperature, the force field is surely a good force field. That sounds also intuitive because it is somewhere in the middle of our temperature ramp. So the takeaway is always train above your target temperature. to make the force field more stable. So with that, I want to finish my talk with the last wrap-up of the training strategies and test strategies focused on chemical reactions. We used the improved dimer method as a first barrier test for usability of the force field in chemical reactions. Next, I introduced the spinning factor for measuring extrapolation of the force field. Big advantage of the spinning factor is it can be directly used during production runs to monitor the reliability of the force field. Also, it is controlled simply by one tag, and it is sufficient not to evaluate it at every MD step. Hence, it has practically no effect on the computational performance. The disadvantage is it does not measure the error directly on energy forces and stress. So one would need for that to still run some DFT calculations on test sets to measure those. And finally, always train above the target temperature in your product runs. So with that, I want to thank you for your attention and goodbye.